We have, so before the tea break, we'll have a talk by Professor Sambuddha Misra. Now, don't need to introduce him much because in the guise of introducing Professor Vijayaraghavan, he has already announced to us that he's worked with an FRS and that he was at Cambridge, right? Well, now he's ISC's problem. So he's going to be talking about hydrothermal circulation. So over to him.
That was quite a cheeky introduction. So I was lucky enough to work with at least one individual who was responsible for discovering the hydrothermal vents in the Atlantic Ocean. And as Dr. Ramdas was talking about, there are very few individuals who have managed to go down to the depths of the ocean and see what's down there. And these were the guys who pioneered the work. And hopefully this will show up. Yep, that shows up. This works. And this works. Okay, so this is going to be a very generic kind of talk where I'm going to talk about how hydrothermal vents are formed, where do we find them, and what's the importance of these hydrothermal vents. And I'm going to take you back to your 7th grade, 8th grade earth science or geography, what do you want to call it, to make you understand what is the importance of the interior structure of the earth in controlling these hydrothermal vent activities. Okay. Now, what are vents? Hopefully the video will play. This is from the NOAA website. And what you will see is that there is, looking at a black smoker, these are huge. They are not a meter high or a 2 meter high units. They are like tens of meters high. And this black smoke is nothing but iron manganese sulfide coming out of these vent systems. And you can see that the water is gushing out. So this water is at around 350 degrees Celsius. There are shrimps living around it, there are crabs living around it. Now you're going to ask me a question, why do we have water at 350 degrees Celsius? Because it's at around 300 bar of pressure. So it's a supercritical fluid, okay? And so there is a huge ecosystem surrounding every hydrothermal vent which is active. The moment the circulation stops, biology disappears. But the mineral which has come out of it stays there. So there is potential in looking into everything that surrounds a hydrothermal system. Now, when we talk about mountains, living in India, we all know about the Himalayas. It's quite big, right? It's one of the largest mountain ranges in the world, but it's nothing compared to what's there under the ocean. This, we are looking at only the Atlantic Ocean system. This is the mid-Atlantic ridge system, coming all the way from the poles to Antarctica. Now, hydrothermal vents are usually found along these mid-ocean ridge systems. Why do hydrothermal vents form? Going back to our knowledge of the structure of the earth. Vinod is sitting there, Atre is sitting there. They're going to correct me if I'm wrong. Okay. It's a layered structure. We have the inner core, which is metallic. Outside of it is the outer core, which is liquid. Then comes the mantle. We have the lower mantle and the upper mantle and the crust. So we can see that the planet is a differentiated body. What do I mean by a differentiated body? It has been partitioned into different sections. Now, if you look at the heat budget of the planet, we receive around 180,000 terawatts from the sun. And there is only 43 terawatts coming from the interior of the planet. But this 43 terawatt is driving this entire hydrothermal circulation. And where is this 43 terawatts coming from? Firstly, there is some of the heat generated in the initial days. What we call the kinetic energy, the heavy bombardment. There were lots of stony bodies hitting us. And kinetic energy getting converted to thermal energy. It's just like getting slapped, okay? If you get slapped repeatedly, your skin will heat up, okay? And slowly the system melts. And once you manage to melt a piece of stone, for a prolonged period of time, I'm talking about millions of years, what will happen, the heavier molecules or the heavier atoms will start dropping towards the center of the system, whereas the lighter atoms will remain at the surface of the system. So the crust, as we know, is enriched in the lighter elements like magnesium, calcium, oxygen, whereas the heavier elements all have dropped towards the interior of the planet. And the core itself is made out of iron and nickel. That's what we think. There'll be no direct sampling of the core. Okay? Now, how has the heat sustained itself? Well, this is not a very conductive body, so there is some of it preserved, and there is also radioactive decay that is going on, so which is giving it some amount of internal heat. Around 4.5 billion years ago, when we started this story, there was a lot of internal heat. And we have been decaying away in that internal heat because the 40 potassium, the uranium-235, they have all decayed away. So they have much shorter half-life than the age of the planet. So we now have around 44 trillion watts of energy to deal with. What happens to that energy? It allows for mantle convection. The mantle itself, if you look at it from a single viewpoint, it's a system which is not moving around. But over a long period of time, it's moving around. That's what we call the mantle convection. The outer core has a much higher temperature, so things sink down, they get heated up, they move upwards, and so forth. So this is a divergent margin, this is a convergent margin. A bit more, I would say, scenic view of this is this mantle plume coming up and then getting diverged. And this is where the new oceanic crust is formed. And this is what the mid-ocean ridge system is all about. Okay? This is where material from the interior of the Earth is coming to the surface of the Earth. Now, whenever we are looking for any exoplanet, a habitable planet, this is the first thing the scientists look for, plate tectonics. Why is it so? Because without plate tectonics, you are not regenerating material at the surface of the planet. So it will be habitable for 1 million year, 100 million year, or 1 billion year. After that, it won't be habitable. So you need a constant supply of material from the interior to the surface for a planet to be habitable over a longer period of time. Now, the manifestation of this is plate tectonics. We all know about it. Plates are moving around, not this fast. They usually move a millimeter to a centimeter per year. And we are averaging this over very fast time scale, okay? Now, hidden underneath all that is the generation of these oceanic crust. If you look at the color coding, the hotter color, the red color, is young oceanic crust. This is in millions of years. And the blue color is very old oceanic crust. All across the Atlantic is the mid-Atlantic ridge. Along the Indian Ocean is the Indian Ocean. This is the Central Indian Ocean ridge, Southwest Indian Ocean ridge, Southeastern Indian Ocean ridge, and then the East Pacific rise and everyone. Now, before we go to the seafloor mountain range, we're going to take a look at what is happening in the Indian Ocean. Why? Because this is one of the things that we plan to explore in the future as an oceanographic community and as an earth science community as a whole. Now, we have the heat budget of the planet. Remember, we have this much of amount of heat coming out. Much of that heat is lost radiatively. Around 32 terawatts is lost radiatively. Only 11 terawatts is lost from the upper mantle as hydrothermal circulation. Now, the hydrothermal circulation can be divided into two flows, the axial flow and the off-axis flow. The axial flow can get up to around 350 degrees Celsius. So it's a very small fraction of the mid-ocean ridge system which has axial flow associated with it. And this axial flow is what we are interested in. Now, we don't need to get to the details of it, how this is all working. For black smokers, which is a kind of hydrothermal vent we saw in the first slide, we have waters at 350 degrees Celsius and around 350 bar with a specific heat capacity of like this. So it can carry a lot of heat with it. Remember, this is not pure water. This is around a 3.2% sodium chloride solution. So these are fluids which are not behaving like liquid water that we visualize liquid water to be. Okay. Now, this is what a plume looks like. This is kind of a white smoker plume. And you can see these minerals popping out of it from every time to time. Now, you might question how much is the entire flux of hydrothermal fluid coming out of the system. The river water fluxes going into the ocean is around 10 to the power 16 liters per year. If you take all global rivers, that's how much water is going from the continents to the ocean, 10 to the power 16 liters. In terms of axial high temperature hydrothermal circulation, we are talking about 10 to the power 13 liters per year. Okay, so there is 3 orders of magnitude less water flowing through these axial vent systems. However, their importance as a controller of seawater chemistry is equivalent to river water chemistry. Why? The concentration of most elements are at least 1,000 to 10,000 times higher than river water. Okay. Now, the known hydrothermal vents are very few. Some are around the East Pacific rise, then there are those in the mid-ocean, mid-Atlantic ridge systems, There are only a few of them identified in the Indian Ocean system. Okay. Now, this is a typical hydrothermal vent, which is a black smoker vent where you have the long chimneys. Water is percolating from the sides through the fissure zones, getting to the magma chamber where it's around 1100 degrees Celsius, the magma. It's reacting with it and it's being pushed out because it's becoming buoyant at a higher temperature. The simplistic view looks like this. Water percolating, getting out of the chimney, then it mixes with the surrounding water. It achieves a neutral buoyancy at a certain depth, which can be a kilometer above the vent. It can be 500 meters above the vent, depending on the starting temperature of the water. So spotting a hydrothermal vent is a very tricky job. It's slightly more complicated than that. Okay, chemistry is highly modified in the process. Seawater is bringing in a lot of elements into the system. Magnesium substitutes for calcium in basalt, so hydrothermal vent fluid is depleted in magnesium and highly enriched in calcium. All the sulfate in seawater gets converted to sulfide, and which forms these chimneys and these black deposits. So one of the classical example of figuring out what is a hydrothermal fluid, if you look at the temperature of the water and the magnesium concentration of it, you can see a inverse relation to it. As the temperature increases, the magnesium concentration goes down. What is an end-member hydrothermal fluid? An end-member hydrothermal fluid is a fluid with zero magnesium concentration. Okay? Now, how to identify a vent? The classical way of identifying a vent is through 3 helium. Why 3 helium? In the modern world, when we look at helium in the atmosphere, it's mostly 4 helium. It is coming from the alpha decay of radioactive elements. And it captures a couple of electrons, becomes 4 helium atom. But when the planet formed, it was primordial helium or 3 helium which was there in the planet. The escape velocity of helium is not very high, so it has been going off from the upper atmosphere. So we have lost all the 3 helium from the atmosphere, almost all, not all. Where it remains in the mantle because it couldn't exchange with the atmosphere. So whenever there is a direct input from the mantle to the ocean atmosphere system, we will be able to find 3 helium. So this is the classical way of figuring out where you have a mantle imprint on seawater chemistry. You look at 3 helium concentration. Herman Craig came out with this idea. Now, all these hydrothermal fluids have transition metals, large amount of transition metals, iron, nickel, copper, zinc, okay. And these transition metals precipitate out as sulfide minerals along the hydrothermal vent or the mid-ocean ridge system. Okay, I should take that around. Now, what is the spatial expanse of hydrothermal plumes? Okay, does it go over a kilometer range? Does it go over 2 kilometer range or 10 kilometers range? Just look at this axis. This is going from 0 to 1000 to 2000 all the way up to 6000 kilometers. And we are looking at the mid-Atlantic ridge system. Anywhere here, we are looking at least a 200 to 400 kilometer range in the spread of the plume. So that is the amount of material is pushing into the seawater system. So these are large scale systems which can generate massive structures of influence. Now remember, these are 3-dimensional systems. We are only looking at a 2-dimensional cross section of it. So there is a lateral and a vertical expanse of it. And usually you can see that they are not exactly at the height of the vent. They can go around it because of the buoyancy problem. Same with the East Pacific rise. This is the East Pacific rise. This is the plume origin, and you can see the material moving away from the continent. What determines the direction of the plume? It's the thermohaline circulation at the depth of the ocean, which is the gravity-driven circulation which is going on below the surface of the ocean, which we don't see with our naked eye. We only see the wind-driven circulation. But the thermohaline circulation determines the direction of the plume. Now, almost every element on the periodic table is being impacted by the hydrothermal system. Anything in yellow is both enriched and depleted. That's a bit confusing, right? How can you both enrich something and deplete something? These elements, high temperature hydrothermal fluid is a source of these elements to seawater. Whereas the low temperature hydrothermal fluid, which we talked about, something below 150 degrees Celsius, is a sink from seawater. For the elements which are in red, they're always enriched. For the elements which are in blue, they are usually depleted. You can see phosphorus, oxygen, fluorine, magnesium, other classical examples. So this is a black smoker. This is an example everybody uses. This is a titanium bottle which is used to sample these black smokers, known as the Von Dam bottle. Karen Von Dam was a PhD student at MIT when she designed this. And once the vent activity stops, you can see this is a chimney which has no biology associated with it. So the moment the heat source has stopped, all biology disappears. It goes and colonizes the next vent where there is still hydrothermal activity going on. Now then there are the white smokers. White smokers are of particular importance because they are 1,000 times enriched in rare earth elements than seawater. So everywhere you find a white smoker, you will find sediments which have rare earths as sulfides associated with them. Now, we talked about this plume reaching a neutral buoyancy and spreading it out. How do we track such a plume? How do we know which direction the plume went, and how can we know what are the resources available in those plumes? We can look at isotope fingerprinting. One of the key isotopes we can use is zinc. Zinc in seawater is at nanomolar level, whereas zinc in hydrothermal fluid is at high micromolar level, almost reaching up to millimolar. So the zinc sulfide that's going to be deposited all around these hydrothermal fluids, especially for a white smoker, will have an isotopic signature which is directly associated with the mantle signature. So we have sensors, chemical sensors, by which we can look at paleo veins. Because remember, less than 1% of the ridge axis will have active vents. If we want to look at vents which have long died but has a lot of mineral deposits associated with it, we need chemical sensors, okay? Because it is impossible to send a manned mission to every point. Now, I'm going to finish with this particular section of my talk, which talks about how hydrothermal vents are important for the origin of life. So on planet Earth, life and death has been fighting with each other for the last 4.5 billion years. And in the last half a billion years that life has been around, there have been 5 major mass extinction events. Either the planet freezes over, or there is catastrophic events like the Chicxulub impact. So every time there is an imbalance in the carbon dioxide budget of the atmosphere, life or complex life disappears from the surface of the planet. Now, my first question to you is that, where do you think life started? Life started long time ago. If this is the entire existence of the planet, around 4.8 billion years, squeezed into a 12-hour clock, we can see that we have been around for less than a few seconds. Okay, dinosaurs were roaming around here. Life started to happening around 3.5 billion years ago. But where did it start? Any idea? Where do you think the first organism lived? Hydrothermal vents. That's an easy one to say because we are talking about hydrothermal vents. And the question is, why hydrothermal vents? Any idea?
Complex chemical reactions.
They are complex chemical reactions. But what is protecting life on Earth in the modern day? Life at the surface of the planet is protected by ozone. We don't get enough UV radiation reaching the surface of the planet. Okay, this is a schematic of how, with time, the seawater chemistry has changed. Every blue molecule is an oxygen molecule. We are starting at around 4.6 billion years ago. There is no oxygen around. The oceans are rich with iron. They're spewing out of the mantle as form of hydrothermal activity. Then photosynthesis starts. Okay, shallow oceans, photosynthesis starts because we still need sunlight. We can't deal with UV, but we still need sunlight to do photosynthesis. As the oxygen comes around, iron +2 is soluble, +3 is insoluble. You oxidize the iron and you start precipitating iron and alternate it with silica layers, which is iron remains soluble. We all know that southern India is filled with these banded iron formations. This is a constant struggle life went through over 1 billion years. I kid you not. 1 billion years, life tried to oxidize the planet, and it repeatedly failed because oxygen was toxic. Slowly and steadily oxygen built up. And if you look at the entire history of the planet, why 4 billion years? Because that's how far the sedimentary records go. We have 2 great oxygenation events. Around 2.8, we had the first whiff of oxygen, and then around 0.8, we have the major whiff of oxygen. How do we know that? We know that, you don't have to get worried about this plot. This is time going in this axis, and this is the sulfur isotope fractionation. What we call this is mass-independent fractionation, and it can only happen as a photochemical reaction in presence of UV. You turn the UV on, you will have mass-independent fractionation. You turn the UV off, you will have zero mass-independent fractionation. Look at the mass-independent fractionation range leading up to around 2.5 billion years. Beyond 2.5 billion years, do we have mass-independent fractionation? No. So do you think UV is reaching the surface of the planet? No. That's the chemical evidence showing that we have created an ozone layer which is shielding the UV. Now UV attenuates within 50 meters of seawater. Visible light penetrates below 100 meters. That's your perfect setting, right? That's your perfect setting where you're shielded from UV, you start life, and then that life from a chemoautotroph becomes a solar power based life form. Now these vent organisms are quite capable of taking, in the modern world, oxygen from seawater, CO2 which is coming out of the mantle, and the sulfide which is coming out of it, and forming sulfate. Okay? This is the chemoautotrophy going on. Normally, this is what we deal with in photosynthesis. This is the kind of aerobic chemoautotrophy that is happening in the vents right now, which is in presence of oxygen. But in deeper vents, we do have the anaerobic chemoautotrophy. This is what we think was the starting material of life at the hydrothermal vents, where we didn't need oxygen, where we didn't need sunlight, and we could start life in the process. Okay? Now, we have talked about black smokers teeming with life, right? And the seafloor mountain ranges that are associated with black smokers are like this. Now we're going to focus a bit on the Indian Ocean. This is the central Indian Ridge, this is the southwest Indian Ocean Ridge, and the southeastern Indian Ocean Ridge. Now we discussed this, we need a mantle convection going on to have a mid-ocean ridge system, and that mid-ocean ridge system will have hydrothermal activity associated with it. But not all ridges are the same, okay? If you look at the central Indian Ocean Ridge, the spread of the red coloration is huge. Southeastern Indian Ocean Ridge, it's even larger. But once you get into the southwestern Indian Ocean Ridge, that the spread of the red coloration is very small. So these are known as the ultra slow spreading ridges. There are no evidence of large-scale mantle activity under these ridge systems. But yet, there are plenty of hydrothermal vents associated with them. So what it tells you is that we have a theory that it's the mantle plume that leads to this sort of what we call hydrothermal activity. But without that mantle plume, such hydrothermal activity is also possible. Okay, so this Southwest Indian Ocean Ridge remains a very enigmatic piece of mid-ocean ridge system that needs to be studied to understand what and how these things happen. So before I end, I need to acknowledge the leaders. John Edmund, he was the first one to look at hydrothermal vents in the Pacific Rise, I think the Galapagos. He was doing seawater chemistry, he was doing depth samplings, and he was finding constant anomalies in iron, magnesium, and zinc. And he thought his measurements were wrong, so he kept doing that for 5 years before he figured out that there was a vent out there. Okay. Herman Craig, he designed the helium sniffing method. The Alvin, we talked about the Alvin, Dr. Ramdas mentioned about it. And Karen Von Dam, who actually was instrumental as a grad student of John Edmund in designing all of these things. And this is Harry Elderfield. Harry was my postdoc supervisor. There I am, with a lot thinner and a lot more hair. Okay, in 2013, 10 years ago, when he won the Goldschmidt Award. So these were the people who had, not me, these were the people who have been instrumental in figuring out the chemistry of the hydrothermal system, not the physics. The geophysicist will kill me if I said that. But last but not the least, any questions? How are they useful?
How can we, they are harmful or impacting the climate conditions?
They are not harmful in climate conditions. There are 2 points to it. It's a constant supply of carbon dioxide to the atmosphere, right? You look at the subaerial volcanic activity, you go, oh my God, it's huge. But this is a 10,000 kilometer mountain chain which has a lot of volcanism associated with it.
Okay.
Without CO2, the global average temperature will be how much? No CO2 in the atmosphere? Any idea? Minus 15 degrees Celsius. So we have a very narrow range of CO2 we need to maintain. And if that CO2 stops pumping, we go to snowball Earth, which is also a mass extinction event. And if there is too much spreading activity, we go to a hothouse world.
Okay. Sir, one more question. So, last month I read one news where it says that we found a hole in the ocean which is Pythias oasis. So, from your presentation, I learned that it is not a hydrothermal vent. But do you have any thoughts on that?
There, in the, I think, Gulf of Mexico, there are large holes in the ocean, right?
Okay.
Where we have extreme high density brine sitting there. So there's an ocean inside the ocean.
Okay.
So, and you can actually see the waves in those ponds because salt is diffusing so slowly that you can maintain such large scale ponds. There might be other holes I don't know about. Yeah.
Okay.
So how sharp is the gradient of temperature? So many of these larger life forms are quite close by, and if you have a 350-degree temperature, these must be something like 50 or so Celsius.
They are surviving, so it's quite sharp. I don't think anybody has measured it
So there
yet.
must be huge convection currents also.
There is huge convection current there. Okay, and if you look at the videos of it that there's a constant plume bringing it up. Yeah.
Sir, two quick questions. One regarding the Permian Triassic extinction. There was one hypothesis regarding that methane vented from the ocean bottom, and it approximately increased the CO2 level at that time. So, any points?
So gas hydrates can collapse and we can have a large flux of methane. But the ocean as a whole does not contain enough gas hydrates to cause a mass extinction. We have seen that in the PETM, where there was a collapse of gas hydrates and we had a large sharp rise in temperature, 5 or 7 degrees Celsius. But you need a mantle input to cause a mass extinction.
And sir, how significant would be the Neoproterozoic oxygen catastrophe in the chain of events you mentioned? Like, was it?
It's toxic, right? To that light form, oxygen was toxic. So there was another mass extinction when oxygen started coming out of the deep ocean.
Okay. Thank you, sir. Thank you so much.
Hi, very nice talk. So the location of these hydrothermal vents, I think, so there are these ridges.
Yeah.
And are these ridges static over time, or there has been some evidence about, because circulations inside the earth can change their directions, right?
Over geologic time scale, ridges have moved around like anything.
I see.
Okay.
I see.
For our perspective, they are quite static.
Okay.
Okay. Like the East African Rift Valley. Sooner or later, in 10 million years, it's going to be a ridge. But for our time scale, it's just spreading apart.
Okay.
Yeah.
Yeah.
Okay, I think we'll close this session and then move on to the next topic. So what we're